Welcome back. Today I want to introduce the idea of Markov chains in the context of solving quant interview questions. Here we're going to assume that there's some sort of working knowledge of elementary probability and statistics, common random variables, just so we can use that machinery in the Markov chain to deduce probabilities. Essentially, we're going to start with some sort of random variable. In this case, we have a Bernoulli random variable that is a simple coin that flips heads or tails with probability p and 1 minus p respectively. And we're interested in all of these questions that, instead of having an independent structure, start to introduce some sort of dependence. And that's going to become a little more clear in a moment. So let's look at question 1. What is the probability of a chain of 3 heads in n tosses? So the key word here is chain. Okay. Question 2, what is the expected number of tosses to see a chain of 3 heads? And question 3, if we were to continue the series of coin flips forever, how often will we see a chain, it's again keyword chain, of 2 heads? And as it turns out, using a Markov chain to model this essentially series of coin flips, that is the idea of achieving a chain of 3 heads, we can actually answer all 3 of these questions relatively easily. But in order to do so, we have to introduce the idea of a Markov chain. So that's what I'm going to do in this video. In the next 2 videos, we're going to answer questions 2 and questions 3. But for now, we're just going to get started with question 1. Okay. So what is the probability of a chain of 3 heads in n tosses? That is this question we're trying to tackle. Okay. And right out the gate, we can see that if we fix n to be some value, then maybe we can get a better grasp on what's going on here, right? So if I say, let's call this event, that is the event of getting a chain of 3 heads, we'll call this event A, okay? And the probability of event A, given n is equal to 1, well, we can find this probability quite easily, right? If we have 1 coin toss, right, and we're looking for a chain of 3 heads, can that occur in 1 coin toss? No, right? So that probability is going to be 0, right? Moreover, if we only have 2 coin tosses, so n is equal to 2, then that is also going to have a 0 probability. All right. Things start to get interesting as you increase n. So let's say that we're looking at n is equal to, say, 5, right? This is going to start to get a little overly complicated very quickly, right? So what is this probability? Well, essentially we have 1, 2, 3, 4, 5 coin tosses. 1, 2, 3, 4, 5. And we're looking for chains of heads, right? So what is one possible configuration of 3 heads? Heads, 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 tails, tails, right? Another possible configuration is maybe heads, 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 right? And then another one would be heads, 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 so on and so forth, right? What I'm getting at here is we could answer this using some sort of combinatorics and maybe law of total probability to derive each of these conditional probabilities for a chain of 3 heads, right? Maybe we can even get some sort of closed form solution such that we can make it, you know, some arbitrary equation and then it all collapses, it looks all wonderful, right? But that takes a lot, right? And there's no guarantee that it's going to simplify into some sort of nice answer here. So we're kind of stuck here in that, you know, we have to go to some arbitrary n, right? And technically it could be infinity. So what do we do here if we're stuck, right? What should we do? Well, we're going to introduce this idea of a Markov chain, okay? So I'm going to get rid of these conditional probabilities, okay? What is a Markov chain? Okay, a Markov chain that is x sub n, a process starting at, let's say, 0 to infinity, is a random variable indexed by n, where the future state only depends on the current state. Okay? So what does that mean? Well, we know very simply, think about in the context of our coin toss example, okay? Let's say we have heads, tails, heads, heads, tails, heads, 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 right? In the context of our coin toss example, right, in order to inform whether or not we have received 3 heads in a row, we don't need to consider the current coin toss in isolation. That is, if I only gave you the outcome of a coin toss, if I just gave you this one, I said, here's a heads, did we succeed in getting 3 heads in a row? You wouldn't be able to tell me that, right? However, what if I gave you, we just flipped a heads, but previously we flipped a tails. So I gave you these two in conjunction with each other, right? Would you be able to tell me whether or not we flipped 3 in a row? Think about that for a second. If I said, hey, we just flipped a coin, okay, we're in this series of coin flips, right? You just flipped a heads, the previous one was tails. Did we succeed in getting 3 in a row? You could tell me right away, hopefully. You could tell me right away, no, we didn't, because we had to restart. We're at 1 heads right now, right? So this is the idea of a Markov chain. That is, the next state is going to only depend on the current state. So if we're currently at a tails, we know that the next state can't be a success. That is, we can't achieve this 3 heads in a row, okay? But this is all kind of abstract, right, without writing it down. So let's write down and diagram this particular Markov chain, okay? Chains are generally defined in terms of states. Okay, so what states would we be interested in modeling this particular Markov chain as? Okay, well, we're interested in a series of heads. So my state space for this Markov chain is going to be, I'm going to call it H0, H1, H2, and H3. So we have 4 states. Maybe you can guess what they are. H0 means we have a chain of 0 heads. H1 means we have a chain of 1 head. H2, chain of 2. H3, a chain of 3. If we achieve this chain of 3, then we're done. So how do we diagram this? Well, typically we write out little circles like this. This will be H0. This will be H1. This will be H2. This will be H3. And what you'll notice is the probability of going, right? This is just like what we wrote out before. If we have tails and heads, we know that we can't go from here all the way to 3 heads in a row, right? Because we just threw a tails. We're restarting from 0, right? So we would say what? What would these 2 states be? If I threw a tails, then the state would have been H0. We don't have a chain. If the next toss was a heads, then we would be in state 1. Okay? And this is how we can go ahead and model this process. Now, if I throw another heads, what state am I going to be in? I'll be in H2, right? It doesn't matter if H2 knows this one. It only matters if H2 knows this one. Why? Because this one knows about this one. And would you look at that? That's starting to look like a chain, hence Markov chain, okay? So using this idea, we can draw the probability of going from one state to another, right? So what's the probability of going from either, state 0 or state 1? We have H0, H1. What's the probability? Well, it's the probability of getting a heads, right? Either we're going to get a heads, which we know occurs with probability P, right? Or we're going to get a tails, and we're going to stay right here with probability 1 minus P. All right, now we're at state 1. What happens? Can we stay in state 1, right? Notice here when we drew this arrow to itself, that's saying that we could stay in H0. If we throw 2 tails in a row, then we don't have a chain of heads. But can we get H1 twice in a row? Well, no, right? Because either we're going to restart the chain or we're going to jump to H2. So we know that H1 is either going to go to H2 with probability P, or it's got to go all the way back to H0 with probability 1 minus P. All right, and what you'll notice is the same is true for H2. It has to either go to H3 with probability P, or it has to go back and reset with probability 1 minus P. And then H3, either we are going to have, what, another H3? Is that possible? Well, technically, yes, right? Because if we have heads, 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 right? This would be, assuming this is tails right here. This would be H1. This would be H2. This would be H3. And we're assuming that we kind of stop this process here. We're not interested in H4. So this would also technically be H3, right? Because we're either looking at this chain of 3 or this chain of 3. So technically it could come back to H3. And it comes back to H3 with probability P. Or it's going to go restart the chain at 1 minus P. Okay? So this is a diagram. This is a picture that represents the states that our Markov chain could be in at any time based on this series of Bernoulli random variables. All right? How do we typically represent this diagram mathematically? Well, we use what's called a transition matrix. All right? And a transition matrix is very important because it makes answering a lot of these questions super, super easy. All right? It's very important. Here are some remarks about the transition matrix. For any entry, we have that any entry of the matrix is going to be between 0 and 1. Essentially, every entry is a probability. Okay? We also have that the sum across the columns is equal to 1. Okay? So that is, if we sum, think about a matrix like this, and we have row, row, row. If we sum, or I guess we're summing across the rows, this has to be 1. We sum across this row, this has to be 1, so on and so forth. Okay? So those are some properties of the transition matrix. But how do we construct it? Well, it's very easy to construct once we have this diagram, which we've already drawn. So let's go ahead and construct this transition matrix. P is equal to, and what we're going to do is we're going to draw a row and a column for every state. So we have H0, H1, H2, and H3, H0, H1, H2, and H3. And to fill this in, all we have to do is ask, what is the probability of going from here to here. That is, what's the probability of going from row to column? Okay, so h0 to h0, what's the probability? Well, we already drew that in the diagram right here, right? It's 1 minus p. So we're going to put 1 minus p. What is the probability of going from h0 to h1? Well, that probability is right here. It's p. And if we know that the sum has to be 1, right? Well, this is a kind of a consequence of it, but nevertheless, we can also look at the diagram, right? Where else can h0 go, right? Can h0 go anywhere? It can't go anywhere else, right? It has to go either to itself or h1. So that means the rest of these also have to be 0, okay? Moreover, what I was getting at before is we know that each element has to be strictly positive, and these guys right here already sum to 1. So based on these two remarks, these two facts of transition matrices, we also know that the remaining elements have to be 0. Okay, now we can just fill this in across the board. Isn't it quite easy? What is h1 to h0? 1 minus p, right? That's this guy right here, right? So we can just go ahead across the board and fill this in, right? h1 to h0 is 1 minus p. h1 to h1, can it stay in the same state? Nope. Probability p, it goes to h2 and then 0. h2 can either go back to h0, 1 minus p, or it can go to h3 with p, right? And then h3 either goes to itself or it goes back to 0. And this right here is our transition matrix. And this is going to let us answer a whole bunch of questions. Whole bunch of questions related to this process, x sub n. All right, so let's not lose sight of the original question. What was the original question? Okay, this was the original question. Okay, I'm gonna bring this down here. All right, what was the probability of a chain of 3 heads in n tosses? All right, that was the original question. How can we answer that using a transition matrix like this? Okay, well, we introduced the idea of a Markov chain to essentially model this process to be able to answer these questions, essentially to come up with this transition matrix. Well, it turns out once you have this transition matrix, it's very, very easy to go ahead and determine the probability of transitioning from one state to another. Okay, and what I mean by that is, let's say that we were curious about going from state h sub 0 to state h sub 3, right, in n transitions. Okay, how would we do that? Well, if we use the Chapman-Kolmogorov equations, this becomes very easy. And this was my previous video, so if you're interested in a rigorous proof, go ahead and check that out. But using the Chapman-Kolmogorov equations, essentially what we're saying is the probability, the corollary is the probability of going from state I, where I is some state in our state space, to state J, once again, where J is some element, the probability is simply going to be the transition matrix, and this is going to be going from state I to state J in n steps, is simply going to be p to the n, the ijth entry. Isn't that easy? So now that we have this transition matrix, the probability of going from state I to state J in n steps is going to be, check it out, p to the n ij, right? But let's hold our horses here, all right? What was the original question? What is the probability of a chain of 3 heads in n tosses? Well, we know, right? We know that the probability of going from, let's say we start in H0, right? Because we start in H0, there is no chain of heads, right? So let's say we start in H0. What is the probability of getting a chain of 3 heads? Well, if you blindly apply this theorem here, then you would say, oh, I know, right? We have n transitions, right? We have n tosses, and we're looking for a chain of 3 heads. I know this state is H3. If I apply this corollary, right, then I know that the probability of, I think we called this event A up here, right? This is going to be event A. Okay, so that's this question we're answering. Then the probability of A is equal to p to the n H0 to H3, which, if we just look at the entries of the matrix, is going to be 0 to 4, right? Because we start here, 0, 1, 2, 3, or I guess depends on how we index it, but let's say we start in H0, we're going to state H3. That's our answer. That is based on, this is by Chapman-Kolmogorov, and we're done. That's the probability, all right? I would say this is kind of like a C plus B answer maybe, because it's wrong. Okay, why is this wrong? Well, what did we answer here? We answered that the probability of going from H0 to H3 in n steps, and sorry, this should be technically big N, because we want to know when we have some arbitrary number of tosses, big N, right? So why is this wrong, right? Well, we're not looking for the probability that we end on a chain of 3 heads. So let me illustrate this to you. Let's say we have n tosses. Okay, why is this wrong? This is wrong. Okay, why is it wrong? If we have n tosses, we have 1, 2, 3, 4, all the way out to n minus 2, n minus 1, n. Okay, so there's 1, 2, 3, 4, so on and so forth, right? Using this as our answer, what we're asking is, if we start in H0, right? We're starting in H0. We may get a heads or tails, heads or tails, heads or tails, heads or tails. That's going to determine our state, right? Let's say we have H0. We could go to maybe H1, H2, H3, then we're back to H1, right? And then we do this until we get to our n tosses. And again, this should be capital N, I apologize. N minus 2, N minus 1, N, right? N tosses. Now we have, let's say we end up in H0, H1, H2. Think about this series of trials, this one realization, right? Is this a success? Is it a success for event A or a failure for event A? Event A being a series of 3 heads appeared in these tosses. This is a success for event A because we have H3 here. That means we saw a chain of 3 heads. We saw it actually on the 3rd toss. Okay? What Chapman-Kolmogorov in this form is saying, this form that I said is wrong, is saying what is the probability that if we start in H3, or if we start in H0 rather, we end in H3. Okay? That is, this sequence evolves as H, let's say, 2, H3, H3. That's one possible sequence. It could also be H1, H2, H3. Okay? So this result right here from Chapman-Kolmogorov, this P to the N, H0, H3, is looking only at this guy and this guy, this last N. What is the probability of transitioning given we start in H0 to H3 after N steps? All right? That means that we're ending on a chain of 3 heads. What's the probability we end on a chain of 3 heads in N steps? That is not the question. The question is, what is the probability of a chain of 3 heads ever occurring in these N tosses? Okay, we're almost there. We only have to modify this a little bit. And what we're going to modify is our original diagram. Okay, so let's go back up here. I'm going to copy this guy. Copy. Come down here. Paste. Okay. So, what the heck, right? What's going on here? I want to be able to, given some capital N, figure out if we've seen a series of 3 coin tosses, right? How can I modify this diagram to ensure that once H3 is hit, we never go out of H3. We stay there. That means we've seen a successful 3 heads in a row, right? How do I do that? How can I model that? Well, instead of giving the probability of leaving H3, what if I just get rid of it altogether? And I say, hey, you know what? Forget it. We can't leave H3. In fact, once we get to H3, we stay at H3, and we never leave H3. H3 is an absorbing state. Okay? There's a lot going on under the hood here. Mainly things to do with accessibility, communication, and transience versus recurrence, but I don't want to talk all about that nonsense. I want to just show you this applied example, okay? What do I mean that H3 is an absorbing state? Well, think about it. If I flip a coin for forever, what state do I have to end up in forever? I'm going to end up in H3, right? If I flip a coin forever, eventually you're going to get a chain of 3 heads, and you're going to be stuck here forever. Okay? That's what an absorbing state is, all right, at least in this particular context. Why is this useful? Because now we can go ahead and capture early on. If we saw H1, H2, H3 early, then it doesn't matter what we see over here. It's going to be fixed. These are going to have to be H3, 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 because once it hit here, we can't leave that state. Okay? So essentially what we're doing now is we're saying that if we use Chapman-Kolmogorov, right, what we're saying is P to the N H0 to H3 is the probability that event A occurs in less than or equal to N steps. Okay? Because keep in mind here, right? This isn't saying that it occurs at what? This isn't saying that it occurs at capital N, right? This is saying in that series forever, right? It occurs somewhere. Do we see that chain? Okay, and this is exactly what we're looking for, right? Does A occur? Let's go back to this original question here. The probability of a chain of 3 heads in n tosses, right? It's the probability of ending up in state H3, right? The probability of ending up in state H3 at any point throughout the n tosses, okay? So this would essentially be the probability of A. Okay? So this is the probability of seeing of a chain of 3 heads anywhere in n tosses. All right, and that is if we remodel the original diagram such that we get stuck at H3. That makes our transition matrix P look like this. We have 1 minus P, P, 0, 0, 1 minus P, 1 minus P, 0, 1, 0, 0, 0, P, 0, 0, 0, P. And then we can use essentially a functional representation here in terms of capital N to discern this probability of a chain of 3 heads occurring anywhere in these n tosses. So this is quite an exciting result, and the reason why I'm so excited is because there are really 3 derivative questions surrounding this one seemingly simple probability question. And the first question we asked was, what is the probability of a chain of 3 heads in n tosses? Well, we just observed that here. By remodeling our diagram with an absorbing state, we found that we can get stuck here forever and compute that probability as that transition matrix raised to the capital N power, and just the transition of going from state 0 to state 3. Okay, that is the probability of getting a chain of 3 heads anywhere in n tosses, right? So if n is 10, what's that probability? We plug in those numbers, we get that value, right? The second question that we observed is, what is the probability that we end with a chain? Okay, that's this guy here. That we end with a chain of 3 heads, right? So if we go back up to what I deemed as incorrect to the first question, via Chapman-Kolmogorov, right? If we use our original diagram, we can answer that question. That's going to be this guy right here. All we have to do is take, using this transition matrix, so this is going to imply some P. To find the answer to Q2, we do P to the capital N, H0, H3, and again, we're deriving it from this diagram. That's going to be the correct answer to number 2. That's the probability we end with a chain of 3 heads, all right? But what about this last question? What is the probability that the first chain of 3 heads happens at n? That is a different question, right? That is a completely different question from number 2. They seem similar, and they're similar, but that's a completely different question. How do we figure this out? Well, let's think about what we know about probability in general, okay? What we're saying here is, this is the probability of a chain of 3 heads anywhere in n tosses, okay? So the probability of 3 heads in less than n is given by what? We say capital P to the n, H0, H3, right? What we want to see is, what if we wanted to figure out if the first time we ever saw it was at the end of the tosses, right? So in other words, right, question 2, let me flesh this out a little bit more. This is question 2, question 3. Question 2 hits 1, 2, 3, ... n minus 2, n minus 1, n, again, these should be capital N's, So when does question 2 hit? Question 2 will hit even if we have H1, H2, H3, as long as this is H1, H2, or H3, so long as we end with H3, question 2, that probability statement is going to hit. We're good. But notice for question 3, it would not hit. We want to be devoid of these first 3, right? That would not hit for question 3. So this would not hit in question 3. Because we want the first chain of heads, 3 heads, to occur at the end. Okay? Well, how can we model that? Fortunately for us, we know about cumulative distribution functions. So the probability of seeing 3 heads in less than or equal to n coin tosses is that. What is the probability of seeing 3 heads in that n tosses? Well, this is just going to be equal to the difference by definition. 3h less than or equal to n minus 1 by definition of a cumulative distribution function. And this is going to be p to the n h0 h3 p to the n minus 1 h0 h3. It's this difference right here. All right, and that is our answer to question 3. In other words, what is the incremental probability that we are gaining of hitting 3 heads with that additional toss? The probability of seeing it in that last 3 tosses for the first time. That's this incremental probability here. That is also the answer to question 3, this guy right here. So it's crazy because such a simple question has so many derivative questions that have to be answered in different ways. So you really have to have a good understanding of Markov chains and transition matrices to be able to answer these questions, right? So remember, question 1, probability of a chain of 3 heads in n tosses. That's easy, right? That's just this transition matrix, right? That's remodeling it with an absorbing state. Question 2, the probability that we end with a chain of 3 heads, regardless of if 3 heads appeared anywhere, right? Anywhere else, we don't care. Then we would just model it as the first diagram, right here. And then this last one here, we model as the difference between the cumulative distribution function that we found in problem 1. That is, if we just take the difference, we find the incremental probability gained from that additional toss. In other words, the probability that we hit 3 heads in a row for the first time on the nth toss. Let's head on over to Python to put a bow on this and simulate all of these to show that they converge to their true analytical solutions that we have written down right here. All right, let's wrap this up. Time to put my money where my mouth is. I'm going to fix n at 10. It doesn't matter what I choose. This is going to be correct for every single n. That's why we solve it for an arbitrary capital N. I'm going to set up this first probability matrix as our first diagram. I'm going to set up this second probability matrix as our second diagram, that is with the absorbing state. This first simulation is simulating coin tosses, and it's going to append an indicator variable to determine whether or not we ever see a chain of 3 heads. The second simulation is going to do something similar, but for question 2. Essentially what it's going to do is it's going to say, hey, did we hit a chain of 3 heads at the end of the coin tosses? So in our last 3 tosses, did we see a chain of 3 heads? And then simulation 3 is saying, if we saw that last chain of 3 heads in our last couple tosses, was that the first time? Was that the first time that we saw it? What's the probability of that? If you go back to the handwritten notes, this is the analog of questions 1, 2, and 3. And then what we see here is, if I keep scrolling down, I think I had to create some new cells so I could keep scrolling. Let's see. There we go. Check it out, right? The simulated probability of seeing 3 heads in n tosses is 0.5. The analytical solution using the transition matrices is 0.507, so it's going to converge. All right? This makes sense, right? Because this is the largest of the probabilities. Okay? The probability of seeing 3 heads at the end of the n tosses is probably less likely, right? And it is. It's roughly 12%, and then the actual is 12.5%, right? Then the least likely of all is, what is the probability of seeing the 3-head chain for the first time at that end? Okay, so the last 3, we get heads, heads, heads for the first time out of every toss. And that's going to be the increment here. We could see it's the difference between the distribution function at n and n minus 1, right? And we could see if we simulate it, we get 0.041, and the solution is actually it looks like 4.29-ish%, so 4.3-ish%. All right. So as you can see, I'll post this in GitHub as a gist if you would like to play around with the simulation. But this is how we can use Markov chains to answer all of these questions. They're all very similar. They're very related to one another, but they're very, 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 they can be very complicated. They can be very confusing. It's very easy to simulate the answers, but what is the actual answer that we're converging to? And that is what we showed analytically. So I hope you enjoyed this video. I hope you enjoyed this introduction to Markov chains in the context of quant interview questions. We're going to tackle the second one in the next video, so stay tuned for that. If you have any questions, again, leave them in the comments below. As always, join our Discord server. We have a lot of interesting conversations there, a lot of interview prep, a lot of interesting conversations, so please join. Check out Quant Guild, check out the courses there. Other than that, thank you so much for watching, and I will see you in the next one.